In this video, we're going to carry on with hydraulic system components. We're going to discuss pumps, valves, cylinders, and accumulators. So when we're taking a look at flow, there's two different types that we're going to deal with: hydrodynamics and hydrostatics. So hydrodynamics we will probably not see in a closed system. This is more of an open system. For instance, hydrodynamics we'll see in a torque converter. When we're dealing with hydrostatics, this is fluid in a confined place. So this is what we want to take a look at first. So one of the things we want to understand is the pump. So there's different types of pumps. So a non-positive displacement pump is, for instance, a scavenge pump, an impeller pump, a water pump. Even though it's turning, it doesn't have to displace fluid. And in a hydraulic system, that doesn't do us any good because we can't build the pressures we need to run the equipment. So in one of these types of pumps, oil is drawn, or air or water is drawn into the center of it, and it's displaced out the outside. Now, if it doesn't displace any fluid, then the water in here will heat up, and this is where you'll see, for instance, in a water pump on a vehicle. But for us, what we need is we need to have a positive displacement pump. So what does positive displacement mean? Positive displacement means for every revolution, the pump will displace a certain amount of fluid, as in oil. So and if we take a look at this picture, this pump displaces 8 cubic inches per revolution, and that never changes. Whether it's doing 100 RPM or 1000 RPM, it still displaces the same amount of fluid per revolution. That is a positive displacement pump. Anytime that we have a positive displacement pump, we also have to have a relief valve in the system because, for instance, if a cylinder dead ends and the pump is still running, that fluid has to go somewhere, so it has to go out a relief valve. So the other thing we need to know is, and we discussed this a little bit earlier in one of the earlier videos, about how many gallons is that? Well, if we have 8 cubic inches times 1000 RPM, that's 8,000 cubic inches. And we divide that by 231 because there's 231 cubic inches in a gallon. And that translates to 34.63 gallons per minute. That's US gallons. Now, if we decide to go to the metric system, again, the conversion is if we do 130 cubic centimeters per revolution. Again, pump rating of 2200 RPM gives us 28,600 cubic centimeters. We divide that by 1000, we get 28.6 liters per minute. So that's the flow rate. And why is it important? Well, it's important to know what the flow rate of the pump is for when we're testing it. And we're going to go into this when we go into testing of equipment. The other thing is, what is the mechanical efficiency of a pump? It would be great if a pump was 100% efficient, but they never are. Because as they start to generate heat, the efficiency goes down. We get what's called slippage or leakage past the pump, and that is wasted energy. So again, every pump style has what they consider allowable efficiency lose. So 90% volumetric efficiency pump has a theoretical delivery of 291.6 liters per minute. So again, when we're taking a look at efficiency, so if it was 100% efficient, and again, that never happens because as a pump runs, it starts to wear and our efficiency starts to go down. So we can go in and we can test what the volumetric efficiency of a pump is with a flow meter. So again, if a hydraulic pump is rated at 100 gallons per minute and is 100% efficient, it will deliver 100 gallons per minute. If that pump was 90% efficient, it would deliver 90 gallons per minute. If we have a loss in the system of 5% when it's 90% due to heat and slippage in the system, then the flow rate is down to 85.5 gallons per minute. So this loss does not change the pump's efficiency, but does change the system's efficiency. And a piston pump should be no less than 90 to 98% efficient, a vane pump 80% efficient, and a gear pump 60% efficient. So in a gear pump, we have a lot of slippage getting past the components. So we're going to take a look at gear pumps first. So a basic gear pump, they're low pressure. Their pressure ratings can go from 1500 to 2500 psi. So we have two gears inside this pump. One's driven and it drives the other pump. So taking a look at this pump here, it's cracked, and chances are someone turned the pressure up, and if the aluminum casting can't handle the pressure, and it just cracks the casting. So you got to stick with what manufacturer says for the PSI rating of a pump. So taking a look at a basic pump, we've got our inlet. This comes from our reservoir. Oil again is forced in here through atmospheric pressure. Now we have two gears in here. One's a drive gear and one's a driven gear. So the drive also runs the driven. So as this is turning, oil is forced around. Now again, remember, a pump doesn't create pressure, it creates flow. It's the restriction to flow that's going to create the pressure. So what happens is oil is carried around from the inlet to the outlet. And if we start to block off the outlet, we increase our pressure. Now what happens internally inside the pump is these two gears are going to be forced backwards against the inlet side of the housing. Again, path of least resistance. It's going to force it back this way. So anytime we're disassembling a hydraulic pump, we should be checking for wear, and always check on one of these because they're considered what's considered an unbalanced pump. They will have wear on these two surfaces here. Now we also have oil in here that will help lubricate the system, but it will still wear, and it'll wear out the bushings or the bearings that are in here as it starts to move. What we have on, again, we talked a little bit about slippage and leakage in a hydraulic system, and what we have is as it starts to build pressure on the high pressure side, it wants to try and get that oil to the low pressure side. So we have these two pressure plates, and what it is on the high pressure side, oil can get underneath these plates and force these plates against the gears, and that keeps it sealed so we get less slippage coming past here. So again, we want to make sure when we're rebuilding a pump and installing new components, we want to make sure we install these plates in the right direction so oil can get in behind it. Oil also gets in and lubricates, because we just run a bushing in these, we want to make sure it gets lubricated. Now, how do we tell an inlet from an outlet of a hydraulic pump? Inlet's always bigger. If they're both the same size, then it doesn't matter which one we have as an inlet and outlet, but these plates may vary, so we can't just indiscriminately just change the direction of flow by inlet and outlet. Other types of internal gear pumps. Again, this is a crescent moon pump, so still we have a drive member that's driving a gear, and this outer gear spins at the same time with it, and again it drives the oil from the inlet to the outlet. And again, this is an unbalanced pump because it wants to force that to the gear side. Again, inlet and outlet ports. Inlet port's always going to be larger. It's better to have more inlet flow than outlet, because otherwise cavitation will occur. Now again, pump rotation, because one gear turns one way, the other gear turns the opposite way. So oil comes in, goes around, and the outlet port. Now there is one style that we call a balanced pump. So they're a vane pump. So what we'll have is we'll have 2 inlets and 2 outlets. Now, because the 2 outlets are 180 degrees apart, we get no oil forcing this gear in any direction because they balance each other out. So this is what they consider a balanced vane pump. The most common place we see a vane pump is power steering systems. And again, we have a cam ring with a rotor and vanes internally inside, and then we have 2 pressure plates. Again, they stay nice and tight so that we don't get any leakage pass from the high pressure side to the low pressure side. The other thing we take a look at is the vanes themselves. So these vanes can come in a couple different styles. They can be tapered. If you take a look at these, they got a sharper edge than the backside, and we just can't reverse the rotation of this because the oil pressure will get underneath that and push that vane in, and it's just not going to build the pressure we require. So we have to make sure if we're rebuilding these, we have to install the vanes in a certain direction. Now, some of these pumps are reversible by turning the whole cam ring upside down, and it will reverse the direction of flow. Another type is a gear rotor or a gear rotor, and again, it works the same principle. As this is driven, it rotates another gear internally to help bring the oil from the low pressure side to the high pressure side. Radial piston pumps. They're big, they're heavy. We don't see them much anymore, but they could still be out there. And how they work is they have an eccentric. So they have an offset cam ring, and what it does is these plungers move in and out. As this pump rotates, these plungers are going to move in and out. And as they've got an inlet valve and an outlet valve, and these are very much the same type of valve setup as we see in an air compressor. They're just a steel plate with a spring behind it. So as the piston goes from the outside to the inside, the inlet valve will open, allow oil to come in. As it goes the other way, the inlet closes and the outlet opens, as long as the pressure that is created internally inside that piston exceeds what the outlet pressure is. Now again, these are very heavy pumps. They're big, and again, you just don't see them much anymore. But what we get to see a lot of, just before we get off this, these can actually stop producing pressure. And what happens is pressure on the outlet builds inside the case and will hold these plungers off the eccentric, and it will go into a less displacement. So we can vary the displacement of certain types of these pumps. The pump that we're going to see the most of is called an axial piston pump. So axial, they're in line. So as the drive is turning, these plungers move in and out off of a swash plate. Now we can have an axial piston pump with a fixed swash plate, or we can have one that's got a variable swash plate. What this means is we can actually bring this, if we have a variable swash plate, we can bring it up so even though the pump is turning, the pistons are not moving in and out, so it's not displacing any fluid. And we usually use one of those in a closed center system, and we'll talk more about that as we get into different types of systems. So taking a look at an axial piston pump. So here's our swash plate. Now this is a fixed swash plate. So as this plunger moves, it will draw oil in, and then as it rises to the top, it'll push it out. Now, anytime we see one of these pumps, we also have to have a case drain. And that's any oil that gets by here under pressure gets to go back to the reservoir. We never want to block off our drain line, because what we'll end up doing is blowing the seal out. This one here is a bent axial piston pump. They can also be a motor. We're going to see axial piston pumps and motors. So what is cavitation? Well, what happens on the inlet side of a pump? if the pump is trying to put out more oil than it draws in, it creates a low pressure on the inlet side. And a low pressure creates a vapor bubble. So what it is oil that's hot will form a vapor bubble on the low pressure side if we get too much of a vacuum. Now this vapor bubble is going to stay like this, and this vapor bubble is going to go around the outside of the gear till it hits the high pressure side. What happens on the high pressure side is once the vapor bubble hits the high pressure, that vapor bubble is going to implode. It's going to collapse. When it implodes, it sends out a shock wave. Now, usually this is near at the pump housing on the pressure side on the end plates. And what it's going to do is it's going to cause some pitting. Now this debris now it can float through the system. Now cavitation is loud in most cases, and it sounds like something's coming apart. So again, if we have cavitation, what can cause it? Well, if we have a restriction on the inlet side of the pump, for instance, say we have a screen that's starting to get plugged, a line that's collapsed, anything that can cause a low pressure to build on the inlet side of the pump is going to cause cavitation. And again, this pressure can be up to 60,000 psi as that vapor bubble implodes. Now, the difference that we have between aeration and cavitation. Aeration, path of least resistance. If it's easier to draw air into the system than oil, it will. So remember, aeration is air getting into the system. Cavitation is a vapor bubble forming in the system from a restriction on the inlet side. Now, will this leak? Maybe not. Again, oil has some fluidity to it, but if it's easier to draw air in through a clamp, it will do that. Now, how would we identify aeration? Well, one of the things we might get, for instance, on a hydraulic cylinder is we might get spongy motion. It might, as it's moving out, be jerky. And that's usually an indication that we have air in the system. So we should be checking all our fittings, all our clamps, making sure that they're all tight so that we don't get the air in the system. So we talked about normally open and normally closed. So in a system like this is a normally open system. So again, going back to our schematic, we have a positive displacement pump, open center system returns to the tank. And we also have a motor here that's reversible. We have our control valve, 3-position. So we can have this motor go in one direction or the other direction. But what happens in the system if the motor stalls out? We have to have a relief valve in the system. So as the pressure in this line builds, it's going to open up this and allow oil, any extra pressure, to return back to the tank. Now let's just say that the pressure in our system is 2,500 psi. When the relief valve opens, this pressure in this line does not drop to 0. It will drop to 2,500 psi and it will stay at that pressure. If the motor starts to turn and the pressure in this drops down to 2,499, this relief valve will close off and not prevent any more oil to be dumped out into the reservoir. If it again rises, it will open again and dump out more. So again, a couple types of relief valves that we're going to take a look at. Here's the schematic of it. Again, we can see that it's closed off. We can also see that it's adjustable, and we can see that the pilot line comes in from here to move it. So here's our adjustment screw. As we tighten the spring, we increase the amount of pressure it takes to lift this ball off the seat. So as the pressure starts to increase in the system, it acts on the surface area of the ball, will lift it off its seat, and allow the oil to be vented out. Another type is a pilot-operated relief valve, and these tend to be a little bit more accurate. So we have a pilot line that goes into control pilot system. Now, as the pressure in behind here is equal, We have a larger surface area here than we have here, so this is going to stay closed. Now what happens is this pilot system, if this pressure gets too high, this pressure is going to bleed off. That piston is going to move up and it's going to dump the extra oil out. Another type of valve we might see is like a one-way check. It's a poppet valve. It's a check valve. We'll see these in different types of systems that we're dealing with. It prevents backflow. We can use it as anti-cavitation valve. When we're dealing with spool valves, there's also rotation direction control valves. So really what we're doing is we're taking oil from our inlet and we're redirecting it to whatever component we want. How we do it, it doesn't matter as long as, again, how it's set up. So when we take a look at a schematic, we wouldn't know that it's a rotary spool valve just by looking at it, because our schematic tells us that this is a closed center system. So pressure builds on this side of the system. So on a closed center system, we're going to use an axial piston pump, and return to tank is closed off. As we start to move the valve, it's going to allow oil to either go out to one side or the other. If we're dealing with a very basic spool valve, again, this is on a closed center system, so inlet from the pump builds pressure. It's not going anywhere because we're not cycling the spool valve. And if you remember from the last video, we have a centering spring that keeps the spool centered so we don't get any leakage out either side. Okay, and again we have a mechanical control valve, so it's being activated through linkage. When we take a look at the grooves that are cut in the spool valve, these are to help lubricate the spool valve, so that they also help seal the spool valve so we don't get a large amount of leakage out past the end. So if we move the spool valve to the left, high pressure oil then can go out to A and move a cylinder or motor. Anything that displaces from A to B, that oil in B is now allowed to return back and out to the base, back to the reservoir. When we go the opposite direction, it does exactly the same thing. Now one of the things we have on a spool valve is a thing called metering notches. Now metering notches allows us to feather a spool valve. We don't want it all the way open or all the way closed. We may want to feather a control. So if we move a spool valve just a little bit, it will allow the metering notches to open. It allows a little bit of oil to come in. It allows us to control the movement of a cylinder to a fine degree. One of the big problems we have is mechanical controls. So when we have mechanical linkage running everything, as these mechanical linkage starts to wear, we start to have greater amount of movement. So again, every time we have a connection somewhere with a mechanical linkage, it's a place for it to start to wear. And we should be paying attention to this, because when a machine's brand new, everything's nice and tight, but as it gets a few thousand hours on it and it's not serviced, these controls now get quite sloppy. So we have to take a look at these and make sure that they stay tight. Now there's another thing that we have is called a detent. So for instance, if I want to move a spool valve, and I can move it and leave it in a position, and it will stay in that position until either we kick it out or some mechanical or electrical device can kick it back into a neutral position. And that we're going to talk about when we get into hydroelectrics. Now pilot operated systems, and this is where we're using low pressure hydraulic fluid to control the high pressure control valve. So for instance, a pilot operated system may run at 300 psi, and all it's doing is providing hydraulic oil to a control valve. The nice thing about this type of system is we're just running small hydraulic lines, much like when we're dealing with air systems. It's a relay setup. So we can have the control valves, we don't have the linkage to worry about. So inside the cab, in our two joysticks, we will have the pilot system, and these lines will go down to the control valve and use hydraulic pressure to move the spool valve back and forth. When we're dealing with electrical switches, so if we have a rocker switch, what we're doing is we're sending an electrical current down to a coil of wire. And what that does is makes an electromagnet. This electromagnet's going to attract the armature and move the spool valve. Now these are either on or off on this style. We cannot vary them, and we're going to talk about how to vary electricity doing pulse width modulation. But at this point here, these ones here are just on and off. If we push the rocker one way, it energizes the coil with 12 volts. If we rock it the other way, it energizes the other one. Or we can have it in the middle where it energizes nothing. We talked about open center and closed center systems. So again, an open center system, the pump displaces the fluid. The fluid is always returning to the tank until we start to block off the flow of fluid, which then creates pressure in the system. If we take a look at the schematic, we know that an open center system has a line that goes all the way through, so we know the fluid is flowing all the time. Compared to a closed center system, which we looked at earlier. Now, single acting hydraulic cylinders. So pressure comes in from the pump, pushes the cylinder up. The load on the top, when we take the pressure away, the cylinder is going to drop back down. We might see this on a gravel truck, for instance. We may have a single acting cylinder to lift the box. And it's the weight of the box when we move the control valve the opposite way that's going to cause this cylinder to retract. And we can have a multi-stage cylinder, and we're going to go more into schematics when we see this is a single stage cylinder. If we have a multi-stage cylinder, it will have a couple different components. So single acting cylinder with a spring, looking at the schematic, even though we have two lines. So again, why does it go back to tank? Well, as oil leaks past the seal here, we can't just dump it on the ground. We can't vent it, so it has to go back to the tank. But this is hydraulically applied, so it extends hydraulically but retracts with a spring. If we're dealing with a multi-stage cylinder, so again, if we take a look at a gravel truck, it'll use a multi-stage cylinder. So as pressure is acting on this large surface area at the bottom, it's able to lift. Now as the first section tops out, then the pressure acting on the second stage is going to lift it up. Now we can have lots of different stages, and again they all work the same way. It's pressure working on a surface area. So when we have a double acting cylinder, okay, so this one here we can tell is double acting because we have two lines going to it. So again, when we push pressure in, we can force this out. Where do we get the maximum amount of force? When we push or pull? Well, again, going back to what we learned earlier, it all depends on the surface area. We have a larger surface area at the bottom of the cylinder than we do at the top of the cylinder. So pushing out, extending the cylinder, is going to have the most amount of force. Taking a look at a basic hydraulic cylinder. So we have the rod end or the piston end. So on the piston end, we have our piston with our seals and a nut, and as hydraulic oil gets in behind this piston, it's going to force this piston to the left. Now on the piston rod end cap, we're going to have a rod bearing. Now these are made out of different material. It can be brass or it can be something synthetic, and it's to help guide the rod and keep it straight in the housing. Then we have a rod seal, which is a pressure seal, and it keeps the oil in there as we're retracting the rod. And we also have a wiper seal, and this is an exclusion type seal to keep any dirt or any debris from coming in and taking out our rod seal. Now, we talked about accumulators and the 3 different types of accumulators. So we can have a weight accumulator, we can have a spring accumulator, and we can have a nitrogen charged accumulator, a gas accumulator. Now, we see mostly in mobile equipment, we're going to see nitrogen accumulators or gas accumulators. And these are to either, we can use them on a suspension, or we can use them for preventing shock loads in the system. And how they're set up is, again, we will have a nitrogen bladder inside and we fill it with nitrogen gas. Why nitrogen gas? Well, nitrogen's inert. We don't want to use air in the system because it can help create an explosion. So we want to use an inert gas, so we use nitrogen. So where do we use something like this? Again, you might see it on a grater on the blade. So if the blade hits a rock, it's not going to overstress the hydraulic system, create too much pressure, and cause line rupture. So the accumulator is going to absorb that shock and let it go back out later. So energy storage, again, that's what an accumulator does. It stores the energy for later use. It also helps even out loads when we start to lift. So we'll use it in a system like that. And again, we might see it on a grater blade. For moving product, if we want to move it smoothly, we can use an accumulator to move anything nice and smooth. As loads vary, again, we can use an accumulator in the system.